Welcome to Science Fair Statistics 101, how to use your statistics in your science project. I'm Harold, a statistics professor and judge at the Science Fair.
Hi, I'm Dwight. I'm also a statistician and a science fair judge.
Hello, I'm Madeline, a statistician and a science fair judge. Slides, please. The objective of this video is to help you use statistics in your science fair project for the 2025 Orange County Science and Engineering Fair. Next slide. This video and the sample slide deck follows the instructions in the Orange County Science and Engineering Fair slide template for science projects. If you would like to follow along with these slides during this video, you can pause the video now and view the resources page in another browser window by typing the link in your browser window, or use your smartphone to scan the QR code. We encourage you to share this video and these resources with your mentor, science teacher, statistics teacher, and anyone else who may be assisting you with your project. Next slide. This video will show what statistical details to include in your science fair project slides and how to report them. For help with how to perform this specific statistical analyses, please see the resources page for links to the online resources. Next slide. Let's start by looking at the slide template for science projects. The first slide in that slide deck has general instructions for formatting your slides. Each slide in the template has specific instructions for what needs to be included on that slide. The 12 slides are ordered from 1 to 12 to help you tell the story of your science project. Next slide. What did you want to know? What did you find? And what does it mean? Next slide. So where does statistics appear in this template? It actually shows up in the results slide on slide 7, as well on slide 8, if you need 2 results slides. Next slide. Your results slide needs to include the data you collected during your experiment, the statistical procedure you used to analyze your observed data and test if the observed data could reasonably be observed under a null hypothesis of no difference. And you need to show charts and graphs of your observed data. Now, Dwight is going to show an example result slide that includes these recommended components. Next slide.
This is the results slide from our sample science project, which illustrates 5 critical components for incorporating statistics well. We'll first describe what these components are, and then explain how we use the research question, hypothesis, materials, and procedure to address each component. Next slide. First, we have a graph that shows the observed data we collected and addresses our research question. Second, we have clear legends and axis labels, including units of measurement where applicable. Third, we have text that explains how to read the graph and connects it to our research question. Fourth, we have the name of a statistical procedure we use to test if the observed data could reasonably have been observed under a null hypothesis of no differences. And fifth, we have text describing why that null hypothesis was or was not rejected. So to recap, on the next slide, a results section that incorporates statistics well includes a graph showing the observed data, clear legends and axis labels, text connecting the graph to the research question, a statistical procedure used to test the null hypothesis, and a sentence describing why the null hypothesis was or was not rejected. Now we'll break this section down in a bit more detail, starting with the next slide. Let's start by looking at a larger version of the graph of the observed data. How do we know what to graph? we should be graphing the association between our independent and dependent variables as indicated on the hypothesis slide, which we show next. Here we can see in the red highlighted text that the independent variable is the solution used to water the plants, and the dependent variable is the height of the plants at the end of the experiment. Next slide. When we make our graph, we put the independent variable, the solution, on the horizontal axis, and the dependent variable, the height, on the vertical axis. Now we could just plot the mean height in each treatment group, but by showing the observed data, we also display two very important pieces of information. First, how spread out the values are within each treatment group. And second, if there were any unusually high or low values that might affect our interpretation of the results. This provides a much richer description of what we actually observed compared to simply plotting means. But how do we organize the collected data in a way that makes it easy to graph? We need a data sheet such as the one shown on the next slide. We are showing this data sheet as you would set it up at the beginning of your experiment. Each row represents a plant, and each column represents something that we want to record about each plant. We show the data sheet for plants 16 through 30 as a separate piece on this slide, but the actual data sheet has 30 rows and 3 columns. At the start of the experiment, we can fill in the values for the treatment in column A and the plant number in column B, but we can't yet fill in the values for height in column C because we have to wait until day 15 to measure the plant heights. We still keep that column reserved for data values we will fill in later. Next slide. Here are some helpful tips for setting up your data sheet. First, give the data sheet a title to identify what information is in it. Second, label each column and include the units of measurement in the label. When you put in numerical data, enter only numbers. If you include the units of measurement as well, computers won't read them as numbers, and you won't be able to plot your data on a graph. So you should include the units of measurement in the label instead. We recommend using the same number of decimal places in every measurement in the same column. And finally, we suggest that you include a picture of your data sheet in the lab notebook section of your project presentation. Next slide. Now we want to know whether the observed effects of solution on the plant height could reasonably have been observed under a null hypothesis of no differences, as shown on the next slide. A null hypothesis of no differences states in general that your independent variable has no effect on your dependent variable. For example, here, our null hypothesis states the choice of solution has no effect on the plant height at day 15. We use statistics to test whether our observed data could reasonably have been observed if our choice of solution truly has no effect on the plant height. Now, there are many tests that we could do even with this one null hypothesis. How do we figure out which test is appropriate? We need to look at our experimental procedures as shown on the next slide. There are two critical things that the experimental procedures tell us. The first is how our plants were assigned to the treatment groups. Here we can see that 10 pots were assigned to get water, a separate 10 pots were assigned to get caffeine, and another 10 pots were assigned to get coffee. Next slide. The second is how the dependent variable is measured. Here we can see that the dependent variable is the height of the plant at day 15, which is a number we can measure. Next slide. When we are comparing the effect of 3 or more treatments, such as water, caffeine, and coffee, on a numerical dependent variable, an appropriate statistical test is called a one-way analysis of variance, or ANOVA. Next slide. Table 2 contains the output summarizing this ANOVA test. The key results in this table are the test statistic, which in this example is an F statistic with 2 and 27 degrees of freedom, its value, which is 55.85, and the p-value, which is less than 0.001. This large of an F statistic suggests a big discrepancy between the observed data and the null hypothesis that the solution has no effect on the plant height at day 15. Moreover, the very small p-value suggests that this large F statistic would be extremely unlikely to be observed if, in fact, the choice of solution did have no effect on the plant height. Thus, we reject our null hypothesis. No matter what test you do, you should always have a test statistic, its value, and a p-value to report. But depending on what test you do and what software or app you use to do the test, you may not get an output that looks exactly like this table. Now my colleague Harold is going to summarize the key takeaways from this video.
So to summarize, first, set up a data sheet beginning the experiment to record the observed data. Next, graph the observed values of your dependent variable within each treatment group. Then, test whether your observed results could reasonably have been observed under a null hypothesis of no differences. Select an appropriate test based on your experimental procedure. And finally, report the test statistic, the p-value, and whether or not the null hypothesis was rejected. You can check out the resources page for information on a slide template for the science projects, slide deck for sample science project, and a slide deck for this video. There's also information on how to set up a data sheet for your data, how to calculate a one-way analysis of variance, and how to choose the statistical tests that you want to use. Please share the information in the resources page with your mentor, science teacher, and/or statistics teacher. There's also information about something called the Science Fair Academy, a series of virtual workshops to guide you through your science or engineering project. Also something called Ask the Scientist Engineer, a set of virtual sessions to ask scientists and engineers questions about your project. Finally, you can read more about special awards for statistical thinking, sponsored by the Orange County Long Beach chapter of the American Statistical Association. And finally, thank you and good luck with your science project.